Okay, I have a cart that's going uphill. I drew him with wheels, but it doesn't really have wheels. His coefficient of friction is 0.1. Though on the screen here it looks like a minus 0.1. That's just because the other equal sign, the part of the other part's equal is not showing rather. Up a 20-degree ramp, going 30 meters a second, uphill as I said. I want to know how far he'll go before stopping. He will have a free body diagram on him. In fact, let me see if I can trace that out. Let's see, let's copy. We'll paste them and we'll move them down to here. If I put my free body diagram on this guy, which I didn't ask you to do, but if I did, that would be mg. And the normal force is going to push him back. By the way, how do I know if this is a right angle? It has to be, by definition. Normal means it's perpendicular to the surface. That makes this the angle. Makes the red guy the hypotenuse. In fact, you know what? I'm going to redraw this guy. Just because I think it'll be clear if I do it this way. Let me pull him straight down. I'll put my normal force here. Please note this is the right angle. This guy here is going to be length of the hypotenuse, which is mg. This here is my angle, theta. So the green guy is going to be the hypotenuse, which is mg, times the cosine of the angle. And if I add red and green together, it will give me, I'm out of colors, we'll go black. Which, of course, is the net force if I have no friction, which will be mg sine of theta. But here's another way to look at it. This is a right triangle, so I know a squared plus b squared is equal to c squared. I can factor out the mg thing here. Oops. And lo and behold, one of your trig identities. We basically just derive that mg sine theta thing. Let's go to the next page. Making the ramp go down, I have mg sine of theta. I have the block moving up, which means that the friction has to be going the opposite direction it's moving, so it's going to be going at the normal force times the coefficient of friction. And both of these guys are heading in the downward direction, which is going to be negative. I know it's negative because I already defined upward to be the positive. If upward was negative, then the initial velocity would be a minus 30, not a positive 30. So what I should end up with is this. The net force on this guy is gravity saying, hey, slow down. Or I should say accelerate in the downward direction. And the friction is going in the downward direction. And that has got to equal to ma. I can factor out an m, leaving me with the acceleration, so let me plug in some numbers. Minus 9.81 times the sine of, what is it, 20 degrees? Minus 9.81. But Mr. Duncan, it's a minus sign here, and yet g is a minus 9.81, so is it a minus minus? I should really add it? No. This minus here is a minus not because of the g. It's a minus because it's the direction that we already defined to be minus, which is whoosh, that way's the negative direction. Let's see, that gives me an acceleration of Okay, so it's going to slow down at 4.28 meters per second. It's going at 30 meters a second right now. Divide that by 4.28, and that will give you the time. From the time, you could then go 1/2 AT squared plus VIT, or you could just use this equation, because you already know what A is. Solve for S, oops, wrong number, minus 4.28. S, therefore, is equal to, well, solve for S. And that's how far it will go before it stops. That's it.